All right, as I was saying, this one of the theories that is currently gained popularity, and when I say it gains popularity, there's evidence, there's actual observational, experimental evidence that shows that this is a possibility. And actually, a lot of it comes from what's called computer modeling. We have these supercomputers where you program in the conditions and then you see what happens with these large scale calculations. But anyhow, these computer models show that in some instances these Jupiter-like worlds, the gas giants, could have interacted with the solar nebula itself. So this is early in the formation of the solar system, that that interaction between with the solar nebula, this material that was still surrounding the early solar system, or any, not just, I'm talking about any solar system, not just ours, where these Jupiter-sized worlds could have actually, because of friction, ended up closer to their sun. So that's a possibility. That is, like I said, has been borne out by computer modeling. So despite the differences between other planetary systems and our own, you get these eccentric orbits, you get hot Jupiters, and super Earths. These systems still, overall, are very consistent with what's called the condensation theory, the idea that there was a giant cloud of gas, mostly hydrogen and helium, in between the stars, and that condensed, and eventually something caused it to start spinning. Some gravitational interaction with perhaps some other star, and so once that happens, of course, this condensation theory has. The angular momentum is conserved, and therefore the spherical object that was the nebula flattens out to a plane. So all of that is consistent with what has been observed, even though the individual solar systems are not like ours, or at least most of them are not like ours. So we still have some work to do in astronomy. That's one of the things that's all the sciences have in common, is that you're still trying to figure out how the universe works, and your job is never quite done, because you might think that you have a really good theory, but then something, you make some other measurement that and you get a result that was completely unexpected. All right, so that's so we, as it says here, we're still trying to figure out how different our solar system is from other solar systems. So we get many types of exoplanets, and so this is just an artist's depiction of a variety of worlds. Usually, I'm actually kind of surprised here. Usually, in these artist depictions, that there's one or two worlds with a nice big ring around it. They're not really showing any of that right there. Just to remind you, of course, I've talked about this already in the chapters about the solar system in general. All the gas giants, not just Saturn, all the gas giants have rings, have ring systems. Most of the ring systems are too small to see from the Earth, but with spacecraft that have gone near these, like Jupiter, for example, has a very, very small ring system. The planet Uranus does as well. Actually, Uranus's ring system it can actually be detected from the Earth, and then of course Neptune also has one. All right, anyhow, it's not being shown right here, but that's perfectly fine. This is an interesting, um, just kind of a broad view of many, many different solar systems. So, these would be stars that are hotter. The stars above this would be hotter than the sun. There's our sun. These are stars that are cooler than our sun. And so, the habitable zone of stars that are cooler than the sun would be closer. The habitable zone of stars that are hotter than our sun, the habitable zone would be cooler. Reminder: the habitable zone is, of course, where liquid water can exist. So too close to the host star, and the water is completely vaporized. Too far from the star, and all the water is frozen. Right? We exist in our star. He puts the habitable zone a little bit closer than where the Earth is, and then all the way out to about the asteroid belt. All right. So this, note that the presence or absence of the greenhouse effect. Is this type of greenhouse effect that's considered the runaway greenhouse effect. Venus is the best example of that. But that this, whether the thickness of an atmosphere, and whether it's a very strong greenhouse effect or a runaway greenhouse effect, will also affect the surface temperature of these stars, and that we don't know about yet. We don't have the ability, although it seems like we will in the very near future, but we don't have the current technology. Does not give us the ability to detect the atmospheres of these exoplanets. Like I said, in the very near future, we hope to have that technology at hand. All right, so let's go over the summary of this chapter 15, which is all about exoplanets. The condensation theory leads us to expect that other solar systems will exist in the same plane. All the planets, all the debris that you find will be in the same plane and orbiting in the same direction, um, you know, around their particular star system. We think that random collisions will lead to irregularities in certain properties. Like, for example, in our star system, Venus is spinning the wrong way, spinning about its axis the wrong way. It's orbiting the sun in the correct counterclockwise direction, but it's orbiting. It's spinning about its own axis as though it's upside down. So that's just one irregularity. Most extrasolar planets, or have been discovered through either the wobble method or the transit method. The transit method is very popular right now, but we still do use the wobble method. Where you're looking for the Doppler shift, the shift in the color of the light of the star. Either in red shifted, which means the star is slightly moving away from us. Blue shifted means it's slightly moving towards us, and that wobble is caused by, it has to be periodic. That's a key thing. It has to be periodic, and when it's periodic, that's caused by a star. By a planet going around that star. All right, the transit method, things have to line up just right so that the planet passes, from our perspective here on Earth, the planet passes across the surface of the star from our vantage point, which doesn't always happen, but it certainly happens enough that we can detect lots and lots of planets using this transit method. In fact, we built very expensive spacecraft to go and measure this. The Kepler mission was one, and of course, the modern mission is called TESS, which I can't remember what it stands for something like transit extrasolar survey or something like that. You can Google it and look that up pretty easily. So we've detected, thousands of these planets. There are thousands more that are strong candidates, which means we have to, when we say that they're candidates, we have to be able to look at these candidates using one or more, more than one method. Remember, there's a third method called microlensing, but conditions have to be just right to be able to see that. About 25% of the systems have multiple planets around the same star, and that's restricted, of course. That's not to say that's a picture of what's out there. That's restricted by our current technology, which limits us to super Earths, right? We don't see anything Earth size or smaller. We see, so things that are. Oops, I didn't mean to skip that last thing. We don't see anything that is, the size of the Earth or smaller, which we think that there's going to be tons and tons of planets that are going to be that size. All right. Let's see. Observations with other systems show them to be consistent with the condensation theory. All right, we've already talked about that. All right, that will be it for Chapter 15.